Okay, 57. Um, let's just again, like I say, I'm sure you'd have read through the question. It says so. Sky Limited operates through an environment where products go through two processes. So, like I said earlier on, when you think of throughput accounting, you're always thinking either I'm looking at mutually exclusive products when I'm trying to get the one with the highest throughput per bottlenecked hour or bottlenecked material, or you're looking at a process and you're working to the pace of the slowest. So you have and I think this one, what I'm going to do here, this is there are 8 machines operating at 90% capacity. Each machine can technically take 6 units per hour. And process Q, 6 machines operating at 85% capacity. Each machine can take 9 units per hour. Now it's interesting because I always visualize this. I don't know why. It's because when we do our washing at home, we don't have a dryer. So we go to the laundrette. So we wash at home, but we do the drying at a laundrette. And the way our laundrette works is that this is the area of the laundrette, and then you have kind of the washing machines here, and then you have the dryers over here. So I'm going to create this exactly the same, and it's funny because it is actually very similar to this picture here. So you have 8 machines. So you have 8 machines. 1, 2, 3, 4, 5, 6, 7, 8, and it says that in those machines, each can technically produce 6 units per hour, but each can take 6 units if you like. So you can have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. You get the drift, I'm sure. Say 6, 1, 2, 3, 4, 5, 6. Just change my pen color so that you can see what's happening with the dryer side of this. And on the dryer, you have 6 machines. And I imagine it's the same in most places that you would have fewer dryers compared to washing machines. I might be wrong. You have 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Think of it that way, that you can have 9 items in each of these dryers. 9 items in each of these dryers here. 9 items in each of these dryers. And like all good laundrettes, from time to time they break down and they don't all work at full capacity. So ultimately, and so you can imagine, right, that what's interesting here is that really, it's really about your one is going to be a bottleneck. Imagine you came in and you literally used up all of this, um, all these machines, and you literally put in all your clothes in here and you did some work, you would then come here and to put all the machines in. So, but the key point is we need to sort of see if they sort of match. When I say match, if there's any restrictions on input, so to speak. So let's look at what's going on here. Over here, you have six units that can go into 8 machines, if you like, operating at a 90% capacity. So maybe one is partially broken down, but the key point here is it's a 90% operational capacity. And if you do that, what you have is 6 times 8 times 0.9, which gives you 43.2. So technically, you could come out with 43.2 kind of items can come out here. 43.2 shirts or whatever. Technically, you should be able to do 48 shirts, but because of a 90% capacity, you would only have 43.2 shirts coming through. As opposed to here, where you have 9 times 6 machines, and I believe it was an 85% capacity. So you have a 0.85 here. So you have 9 times 6 times 0.85, and that gives you 45.9. So again, because it's a process, you're washing clothes, right? You wash the clothes and then you have to dry them. So doesn't matter if you decide to go along and you can't even do 45.9 here, even if you could. You're still restricted. So the key point here is that we operate at this pace, if you like, because you can't even fit in 45.9 in here. The capacity isn't available. That's the best you can do if you want to keep things, if we don't want any waste. And this is important, you'll see in the next question. So we know, therefore, that we must work to the pace of the washers. Okay, great. So that's the first thing you know. That's kind of helped you work that out. Well, let's look at the contribution situation. So we know we're going to have to work to the pace of process P. Let's look at that. So it tells us that so because we're working to that pace, that's technically our throughput. That's the throughput. That's what's coming through. That's what we're working through to. So it tells us that our selling price, what they're going to do is they're going to do a selling price of 20. They're going to do a 15% discount, apply a 15% discount. So 15% takes off £3 of that, leaving selling price of 17. And then it tells us the material cost is $5. That's what we need. We're not interested in anything else. This is throughput, and therefore our throughput, if you like, per unit is $12. And we know they tell us that it currently takes 0.2 hours to make, if you like, an item. So therefore, if it's taking 0.2 hours to make one unit, therefore we can spend for 1 hour, we can therefore do 12 divided by 0.2, which would take us to $60, if you like, per hour, right? Because it's $12, if you like, for every unit. And currently we're making one unit at 0.2 hours. And so that's how you sort of deal with it, really. So you can see that we kind of, sometimes you might get a question that just wants you to focus on you almost need to go through the steps to see where the bottleneck is and then work to that. Okay, let's look at what's going on here. 58. What is the throughput accounting ratio? So typically let me find the return per hour first, and then I'll find the factory cost per hour, and then I can find the throughput ratio, right? Because that's that divided by that. So what's my return per hour? My return per hour must be my sales, which is 9 grand. Thank you very much. Minus my material cost. Listen to what I said. My material cost. I didn't say cost of sales, not material used, not the 800 kilograms. So don't say 800 divided by 1,000 times that, doing your proportion. This is lean accounting. You shouldn't have any waste. You should only be buying in inventory that you will use. So it's your problem that you've bought more. So it literally treats everything from a lean accounting point of view. So it's minus 3,000, which gives you throughput of 6,000. Time, maximum time available, nicely matches time taken. So you have used up all that time, and therefore you have 6,000 divided by 200, and so you have 30 pounds. Your return per hour is £30 per hour. Your factory costs, we can see here your labor costs and your overheads, which are 2,000. Remember, labor costs are now considered to be a fixed cost. Plus 1,500, that's 3,500. And divide that 3,500 by the total number of hours, which is 200 hours there again. So 3,500, because it's fact, right? 3,500 divided by 200 is 17.5. And so we have this as 17.5. So what does that mean? Our TPAR must be the 30 return per hour divided by the factory cost per hour. 30 divided by 17.5 gives us 1.7. I get 1.714, but that rounds. That looks like 1.7. Okay, great stuff. I thought this was a cheeky question, but you had to watch it carefully. It's funny because hours might not be the only restriction. Sometimes demand, it's important to look at this again. Demand might be the restriction here. I'm sure you've looked and done this question, so I'm just going to jump straight in. So it says daily demand for product X is 10 units and daily demand is 16 units. So these are the hours available per day. Initially, you want to sort of think, oh my goodness, they're not going to be enough hours. But if you look at it carefully, if this is the maximum demand here, in these two scenarios, let's look at that. It's just good to check these things. Look at this to see if it's even a restriction. You're using 1 hour to make a unit, so that's 10 hours there, and of course 16 units here. So this is 10, and 0.75 times 16 happens to be 12. So actually, you have enough time to make this process one has enough time. There are enough hours. There is no bottleneck, if you like, given the demand that you have. Let's look at C, the 3 as well. Here again, you have 10, And here 0.5 times 16 is equal to 8. So here again you need 18 hours. You have 18 hours. So 1 and 3, there's enough time for 1 and 3. 1 and 3 are not your problem. When you look at this one though, you have here 7.5, and then you have here times 16, you have 16, you have 23.5, excuse me. And so that's 1 hour greater. So you need more hours. So this is where the bottleneck is technically. So if you're trying to improve anything, you don't need to improve anything here or here, really, because there's enough time. So it's increasing the efficiency of the maintenance routine for process 2. If I can increase efficiency, it means I can spend less time making these products. So that will definitely help. Increasing the demand for both products, well, no, you're still restricted by, if you like, well, hours available, and you don't have, in terms of improving throughput, you don't have any more hours, so that won't help. Reducing the time it takes for rest breaks in process 3, well, you don't have to reduce the rest breaks. You have enough hours. You might even start seeing some inefficiencies. And reducing the time product X requires for process 1, it doesn't, no, that won't make things more efficient. Our problem really is what's going on with process 2. Really, ultimately. So we need to do better. Either we get more time for product 2 if we want to improve throughput, or minimize this so that we can actually get all these units through. So the answer here is 1, right? And that's really literally by looking at the time available, and 1 and 3 have enough time, 2 doesn't. So it's about trying to improve efficiencies with 2 and not worrying so much about 1 and 3. Okay, great stuff. Right, yes, okay, I think I'll stop there, and I'll do the next 2 questions in the last video.